on land. Changing currents let the oceans absorb CO2 from the air. That cooled the southern hemisphere and unleashed the immense power of glaciers such as the Franz Josef, which advanced down this wide valley, filling it with deep, thick ice. Now, we're flying over today's coastline, where giant boulders are leftovers from that last ice age.
A glacier is a great earth-moving machine. It's a dump truck that carries rocks that fall on top of it. It's a bulldozer that pushes rocks in front of it, and it outlines itself with those rocks, making a deposit that we call a moraine that tells us where the glacier has been. We're 20 kilometers, 12 miles from the front of the Franz Josef Glacier today. But about 20,000 years ago, the ice was depositing these rocks as it flowed past us and out to sea.
The rocks we can still see today confirm where the glacier once was. Now, in a computer-generated time-lapse condensing thousands of years of Earth's history, we're seeing what happened. Lower CO2, colder temperatures, more snow and ice, and the Franz Josef advanced. 20,000 years ago, 30% of today's land area was covered by great ice sheets, which locked up so much water that the global sea level was almost 400 feet lower than today. Then, as Earth's orbit changed, temperatures and CO2 rose, and the glacier melted back. The orbits set the stage, but by themselves they weren't enough. We need the warming and cooling effects of rising and falling CO2 to explain the changes we know happened. Today, atmospheric CO2 is increasing still more, temperatures are rising, and glaciers and ice sheets are melting. You can see this clearly on the lake formed by the shrinking Tasman Glacier across the range from the Franz Josef.
This is what the end of an ice age looks like. Glaciers falling apart, new lakes, new land, icebergs coming off the front of the ice. In the early 1980s, we would have been inside New Zealand's Tasman Glacier right here. Now we're passing icebergs in a new lake from a glacier that has mostly fallen apart and ends over 6 kilometers, 4 miles away.
One glacier doesn't tell us what the world is doing, but while the Tasman has been retreating, the great majority of glaciers on the planet have gotten smaller. This is the Columbia Glacier in Alaska. It's a type of glacier that makes the effects of warming easy to see. It's been retreating so fast that the Extreme Ice Survey had to reposition their time-lapse cameras to follow its motion. In Iceland, warming air temperatures have made this glacier simply melt away, leaving streams and small lakes behind.
Thermometers in the air show warming. Thermometers in the air far from cities show warming. Put your thermometer in the ground, in the ocean, look down from satellites, they show warming. The evidence is clear. The Earth's climate is warming.
This frozen library, the National Ice Core Lab in Denver, Colorado, has ice from all over, kept at minus 35 degrees. The oldest core here goes back some 400,000 years. Here, really ancient ice from Greenland in the north and Antarctica in the south reveals Earth's climate history. Let's see what cores like this can tell us.
First are those layers I mentioned in the New Zealand snow. They've turned to ice and we can count them. Summer, winter, summer, winter. Like tree rings, we can date the core. Other cores tell other stories. Look at this. It's the ash of an Icelandic volcano that blew up to Greenland 50,000 years ago. Cores hold other and even more important secrets. Look at these bubbles. They formed as the snow turned to ice and trapped old air that's still in there.
Scientists now are working with cores from Antarctica that go back even further. They tell us with a very high degree of accuracy how much carbon dioxide was in the air that far back. Researchers break chunks of ice in vacuum chambers and carefully analyze the gases that come off. They're able to measure very precisely levels of carbon dioxide in that ancient air.
Looking at the cores, we see a pattern that repeats. 280 parts per million of CO2, then 180, 280, 180, 280.
By analyzing the chemistry of the oxygen atoms in the ice, you can also see the pattern of rising and falling temperature over time. Colder during the ice ages, warmer during the interglacial periods. Now put the two lines together and you can see how closely temperature and carbon dioxide track each other. They're not exactly alike. At times, the orbits caused a little temperature change before the feedback effects of CO2 joined in.
But just as we saw in New Zealand, we can't explain the large size of the changes in temperature without the effects of CO2. This is the signature of natural variation. The cycle of the ice age is driven by changes in Earth's orbit, with no human involvement.
But here's where we are today. In just 250 years, since the Industrial Revolution, we've blown past 380 with no sign of slowing down. It's a level not seen in more than 400,000 years, 40 times longer than the oldest human civilization. So physics and chemistry tell us that adding carbon dioxide to the atmosphere warms things up.
And Earth's climate history shows us there will be impacts, from melting ice sheets to rising sea level. But how do we know with equal certainty that it's not just more natural variation, that humans are the source of the increasing CO2?
When we look at a landscape like this one, we know immediately that volcanoes put out all sorts of interesting things, and that includes CO2.
So how do we know that the rise of CO2 in the atmosphere that we see comes from our burning of fossil fuels and not from something that the volcanoes have done? Well, the first step in the problem is just bookkeeping. We measure how much CO2 comes out of the volcanoes. We measure how much CO2 comes out of our smokestacks and tailpipes. The natural source is small. Humans are putting out 50 to 100 times more CO2 than the natural volcanic source. We can then ask the air whether our bookkeeping is right, and the air says that it is.
Volcanoes make CO2 by melting rocks to release the CO2. They don't burn, and they don't use oxygen. But burning fossil fuels does use oxygen when it makes CO2. We see that the rise in CO2 goes with a fall of oxygen, which says that the rising CO2 comes from burning something.
We can then ask the carbon in the rising CO2 where it came from.
Carbon comes in three flavors. The lightweight, carbon-12, which is especially common in plants. The medium weight, carbon-13, which is a little more common in the gases coming out of volcanoes. And the heavyweight, carbon-14. It's radioactive and decays almost entirely after about 50,000 years, which is why you won't find it in very old things like dinosaur bones or fossil fuels. We see a rise in carbon-12, which comes from plants. We don't see a rise of carbon-13, so the CO2 isn't coming from the volcanoes. And we don't see a rise in carbon-14, so the CO2 can't be coming from recently living plants. And so the atmosphere says that the rising CO2 comes from burning of plants that have been dead a long time.
That is fossil fuels. The CO2 is coming from our fossil fuels. It's us.
So physics and chemistry show us carbon dioxide is at levels never seen in human history. And the evidence says it's all of us burning fossil fuels that's driving the increase. But what about climate change and global warming? Are they for real? Here's what those who have looked at all the data say about the future.
Climate change, energy security, and economic stability are inextricably linked. Climate change will contribute to food and water scarcity, will increase the spread of disease and may spur or exacerbate mass migration.
Who do you suppose said that? Not a pundit, not a politician, the Pentagon.
These war games at Fort Irwin, California provide realistic training to keep our soldiers safe. The purpose of the Pentagon's Quadrennial Defense Review, the QDR, is to keep the nation safe. The review covers military strategies for an uncertain world. The Pentagon has to think long-term and be ready for all contingencies. The 2010 QDR was the first time that those contingencies included climate change. Rear Admiral David Titley is oceanographer of the Navy and contributed to the Defense Review.
Well, I think the QDR really talks about climate change in terms that it really isn't for debate. And you take a look at the global temperatures, you take a look at sea level rise, you take a look at what the glaciers are doing, not just one or two glaciers, but really glaciers worldwide. And you add all of those up together. And that's one of the reasons we really believe that the climate is changing. So the observations tell us that. Physics tells us this as well.
What climate change means for key global hotspots is less clear.
We understand the Earth is getting warmer. We understand the oceans are getting warmer. What we do not understand is exactly how that will affect things like strong storms, rainfall rates, rainfall distribution. So yes, climate change is a certainty, but what is it going to be like in specific regions of the world and when?
One area of particular concern to the Navy is sea level rise.
Sea level rise is going to be a long-term and very, very significant issue for the 21st century.
The QDR included an infrastructure vulnerability assessment that found that 153 naval installations are at significant risk from climatic stresses. From Pearl Harbor, Hawaii to Norfolk, Virginia, the bases and their nearby communities will have to adapt.
Even with 1 to 2 meters of sea level rise, which is very, very substantial, we have time. This is not a crisis, but it is certainly going to be a strategic challenge.
Globally, climate change is expected to mean more fires, floods, and famine. Nations may be destabilized. For the Pentagon, climate change is a threat multiplier. But with sound climate science, Titley believes forewarned is forearmed.
The good thing is the science is advanced enough in oceanography, glaciology, meteorology, that we have some skill at some time frames of predicting this. And if we choose to use those projections, we can, in fact, by our behavior, alter the future in our favor.
Titley and the Pentagon think the facts are in.
Climate change is happening, and there is very, very strong evidence that a large part of this is, in fact, man-made.
Aid with some of the CAS evac.
The military is America's single largest user of energy, and it recognizes that its use of fossil fuels has to change. The Pentagon uses 300,000 barrels of oil each day. That's more than 12 million gallons. An armored Humvee gets 4 miles to the gallon. At full speed, an Abrams battle tank uses 4 gallons to the mile. And it can cost as much as $400 a gallon to get gas to some remote bases in Afghanistan. Fort Irwin is a test bed to see if the Army can operate just as effectively while using less fossil fuel and more renewables. And it's not just Fort Irwin and the Army. At Camp Pendleton, Marines were trained on an energy-saving, experimental forward operating base that deployed with them to Afghanistan.
Before any equipment goes into theater, we want Marines to get trained on it. So what are some of the things that we could take hold of right away and make sure that we can make a difference for the warfighter downrange?
They test out different kinds of portable solar power units. They also practice how to purify stagnant water and make it drinkable. The Army and Marines both want to minimize the number of convoys trucking in fuel and water.